Hello, and welcome to my presentation titled Smarter Simulation Design and Modeling to Improve Bulk Material Handling Equipment Performance. I'm Andrew Grimer, and I'm the Chief Operating Officer of Bulk Materials Engineering Australia, and also an application engineer for Altair EDEM. Just want to provide a quick overview of my presentation today. So I would just like to introduce firstly by talking a little bit about some of the traditional design methods and application of advanced modeling technologies used to design bulk material and handling equipment, and talk about some of the design and simulation processes deployed by engineers during the design of equipment, and talk a bit about material testing and DEM calibration, and also discuss multi-physics and various Altair solutions which can be utilized to model very complicated bulk material handling applications. And then also look at an industrial case study where Altair EDEM has been deployed to help in the process of identifying material flow problems and debottlenecking a mining operation to increase annual throughput. So traditional design methods can be utilized in the design of a lot of material handling applications, but in some applications can be quite limited in terms of their capability. But we need to utilize these methods initially when designing any material handling equipment, such as hoppers or feeders or transfer chutes, for example. These methods typically rely on quasi-static flow properties and rules of thumb, where you can see an example of the application of continuum modeling to model the rapid flow of material through this chute, where we look at things like trajectories, angles of impact, material velocity, material stream thickness, and things like that. But they're quite limited in terms of the 3D visualization to examine very complicated scenarios where DEM has greater capability to model the presentation and complex flow of material. So these continuum methods are generally based on lump mass analogy. They have limited capability to model highly cohesive materials, and sometimes they can be a little bit tricky to apply to complex geometry. So sometimes it can take a little bit of time to set up the equations, but they solve very quick compared to sometimes DEM results, but limited capability. So this is where we can use advanced, flow modeling technologies. So if we want to obtain a reliable and an optimum outcome with our equipment design and operation, it's imperative that we start that design process, looking at especially at the critical components that may be problematic for the whole system during the early stages of the design process. Okay, so it's like identifying constraints like geometric constraints with offsets, certain limitations in drop height and things like that. Sometimes things like, for example, transfer chutes and hoppers and silos, and that sometimes they're not given enough attention to detail during initial feasibility studies and things like that, and that can lead to suboptimum operation during the when things are designed and installed, because there was a lot of constraints during the initial design process that weren't really considered and optimized. Okay, so but to do this simulation modeling, we need reliable tools that can accurately predict and control the material flow throughout the handling and transfer processes. And this is where discrete element modeling is very handy for this situation, because of its capability to model discrete material, and it also has mathematical models which incorporate bulk material properties, and also the constraining geometry of equipment. So by utilizing these simulation tools, we can increase throughput, increase reliability, reduce housekeeping and maintenance issues. We can have improved plant and equipment layout and flexibility. So by looking at various design solutions, we can see which one provides the best solution that is that is very robust. It also allows for longer continuous operation under steady state conditions. So these days, a lot of mining operators are pushing for better productivity and lower operating costs, and want to have very large windows where equipment will operate before they're shut down for maintenance. So there's a lot of pressure to make sure that a robust design is developed and installed, and this is where simulation tools come in handy for that. So Altair EDEM has been used in a wide range of mining applications. Some of them are just shown here, but there are a lot more where it's been utilized, such as transfer chutes for fixed and mobile equipment. Also, in processing equipment, may also be in transportation or haulage or unloading equipment, such as dump trucks discharging material into ROM bins. Looking at understanding the flow behaviors and the loads exerted from that material flowing into the bins. It may also be looking at train, wagon, rotary unloaders, as you can see on the screen here, where you're looking at the torques and the loads and the flow patterns as that cell rotates. So generally, the design and simulation process that we recommend in order to come up with a reliable and robust design is that initially we start off by developing a 3D model or of our existing equipment, for example, or even if it's a new plant, start to do the plant layout so we can identify constraints. It's very useful sometimes to conduct 3D scans to get a good representation of what exactly exists in the building or our equipment. So we've got a good working base to start the design off. Then from there we can identify some constraints if we have head height restrictions, critical infrastructure or structural elements in the way that we need to avoid. We also need to identify the objectives of this design. Are we trying to increase throughput? Are we trying to reduce wear, blockages, spillage, or dust? Okay. And we also need to characterize our bulk material. There is a lot of projects that I've worked on before where equipment has failed because there hasn't been a good understanding and appreciation for the bulk material properties. Okay, so understanding bulk density variations, understanding the change of internal cohesion and friction and wall friction with our moisture content. Understanding how sticky and cohesive or how free flowing our material will be, or even the particle sizing can lead to fatal flaws and design failures. Okay, so we also use this material testing to help develop our mathematical models or our calibrated EDEM material models that we use for our simulation modeling. Okay, and we can utilize various tools that Altair have to assist with the calibration, such as calibration kits, which use a range of standard tests that we can utilize, and also various platforms like HyperStudy and tools like EDEM just to help with that automated process of calibration. Then from there we can start to develop our designs. Okay, so essentially when we start our process, we will just develop a simple CAD model. Sometimes it might be just a simple surface model just to get the process started. Then we can look at refining it, and we may initially select this design based on traditional design and continuum methods. And then we can utilize Altair EDEM tools to examine the performance of this equipment under various operating conditions. So one of the great capabilities with DEM is the fact that we can look at various conditions like different throughputs, different operating speeds, surge conditions, different bulk materials, and assess how that equipment will perform. we can also conduct, multi-physics simulation too, if we want to couple our DEM models with other physical disciplines as well. Then we need to evaluate our results and assess if our design is optimum, or if there are potential regions or areas of the design that need to be refined. This may be changing some geometry to improve presentation, or reduce power or torque, and then we can we can iterate on these designs by changing the CAD models and our designs, and then evaluating them via simulation. Then once we have come up with our final design, then we can move on to detailing of that design, and move forward to fabrication installation. But typically what we like to do is to do a final check on that design by running a final simulation, just to make sure that during that final detailing process that things weren't excessively or there wasn't too much variation with that final design before give the final tick before we move into fabrication of that final design. So in a lot of industrial applications, we typically have physical behavior that can happen simultaneously. Okay, so multiple disciplines happening at the same time. So look at this this dragline bucket system, where we have the bucket digging into the bulk material. We have loads exerted on the bucket. We have we also want to examine material flow and the carrying capacity or load capacity of that bucket. So what we can do is we can couple discrete element modeling with various other tools like multi-body dynamics, FEA, CFD, and also with artificial intelligence. So this basically reduces the need to make assumptions on, for example, bulk material loads that may be present when conducting FEA analysis, multi-body dynamics analysis, and even CFD. Okay, so this way we can actually get accurate load predictions, and also get better distribution of loads on our equipment, which also enhances our FEA capabilities if we're using tools like OptiStrut or SimSolid. Another important aspect when designing bulk material handling equipment is dealing with wear. A lot of bulk materials tend to be quite abrasive, requiring heavy-duty wear liners to sustain the wear and maximize the life of that equipment. So what we want to do when we're conducting our material flow modeling is to get an idea of regions where we expect higher maybe abrasive wear, where we can utilize models like the arched wear model or impact wear using the OCCA model to assess the regions or the hotspots for wear. And this can help us to select our liner packages, what thickness of liner we require to achieve a desired life. And these capabilities, by modeling this up front, this helps with the overall performance and longevity of our equipment. So here just shows an example where we're looking at the wear predictions on this lower spoon of this transfer chute. So this is just a previous project, and you can see there that the predictions from our DEM model, especially with the arched wear, where we're seeing a lot more abrasive wear, aligns quite well with what we saw in a loading spoon in real life, where we could see the same sort of similar profile with wear, and also the life that we expected. So we're sort of predicting that this spoon would last approximately 12 months. So I just want to have a look at a case study. So this is a case study where we looked at debottlenecking and optimizing bauxite mining operation. So the mine wanted to increase its annual throughput up to 13 million tons per annum, and this required the throughput on the various parts of the mine to be increased. So looking at increasing the throughput through the crushing plant and overland conveying system from 1,500 tons per hour up to 2,150 tons per hour. So to do this, we needed to increase the speeds and the capacity of various processing and handling equipment, such as conveyor belts. And as a result, if we start to increase the speeds of conveyor belts, we start to change the trajectories and the flow of material through transfer points. So we want to examine, which transfer points would be potentially problematic and need to be redesigned or potentially modified to handle these higher throughputs and reduce the potential risk of downtime and blockages and spillage and excessive wear. So here's just a quick overview of the mining operation, where we have our crushing plant, and then we have a series of overland conveyors which transport material from the crushing plant to a stockyard where it is stored, and then it is reclaimed and then sent to the ship loader via a series of conveyor belts. So to begin this project, what we did first was conducted some material testing to understand the material properties, and we collected a representative sample of our bauxite, which is imperative that we actually get a good representative sample. And then we conduct some test work to assess the strength of our material at various moisture contents. Okay, so what we did here was looking at the moisture content that displays the worst handling characteristics, and also looking at another maybe lower moisture content where material may be a little bit more free flowing. So we can develop a couple of different material models at different moisture contents and conditions to comprehensively evaluate the performance of our equipment. Then we also need to conduct some material testing for DEM calibration purposes, where we conduct some specialized tests that look at the particle-to-particle interactions, as well as particle-to-equipment interactions, looking at things like wall cohesion and friction. So we utilize these tests to develop our material models. So once this testing is completed, we can commence our material model calibration, where we firstly define our particle shapes. So within EDEM, we recommend using multi-spheres or polyhedral particle shapes. And then once we've developed our particle shapes, we need to assign a particle size distribution, which we can easily do. Then we select a contact model. So we've selected a cohesive contact model, which best represents this bauxite material we're modeling. And then we commence our calibration process, where we basically simulate in a virtual environment the real-life physical test that we conducted in our laboratory. This is just showing one example. So what we do is we iterate these simulations with different contact model parameters and mechanical parameters to see which parameter set best correlates to the real-life dynamic behavior. And we can utilize tools like EDEM Cal or HyperStudy to assist with this iterative process. And then once we've developed our material model, then we can start our simulation modeling process. So here's just looking at one of the transfer chutes as part of the crushing plant facility. So this transfer chute feeds material from this upper conveyor onto this lower incline conveyor that goes into the crushing plant. Okay, so this chute has a lot of problems with build-up. You can see here, this is the transfer chute where there's rubber curtains installed to try to minimize build-up. But the biggest problem with this chute was the excessive belt wear. Okay, so the belt was only lasting about 8 to 12 weeks before it needed to be replaced, and that was due to a lot of material boiling in the loading zone. So it's basically a lot of material just staying stagnant in that loading zone that slides across the belt and then gets under the skirt plates and causes a lot of wear along the edge or under the skirt plate. We see these like tram lines created. And there's also spillage issues that require consistent or continual housekeeping to wash away that build-up. So what we did first is that we conducted a DEM simulation of our existing design. to help verify the accuracy of our model, but also to identify the potential causes of the problems of this transfer chute. So you can see from this simulation, we were able to model that, that boiling of material and carryback that we see occurring at the low point. Also, you can see here we have a lot of material that is actually stagnant or building up along the skirt plates that leads to that accelerated wear. And we've got direct loading onto this inclined belt, which isn't ideal for for supporting the belt and keeping your skirt gaps or clearances quite consistent. So then once we identified those problems, we started our design iteration process where we looked at multiple different solutions and assessed which solution would be the best performing. And what we did here is with this design is that we installed a soft loading curved spoon, which helped to minimize the direct loading on the chute, but also kick the material forward in the direction of flow to minimize that material flowing back down towards the transition. And we also wanted to, increase our skirt clearance or our edge clearance on the belt, so keep the material as far away from the skirt plates and the seals as much as possible. And this was achieved by, making some modifications to the belt profile and the idler supports underneath. So you can see with this design, we also looked at, modeling the wear to try to predict how long the spoon would last for. Also trying to select the best thickness of the liners required to achieve a good life, and also just changing some of the geometry of this spoon to maximize life. So with this chute, we modeled both the impact wear and abrasive wear. And we predicted that we'll get approximately 12 months of life out of this chute. So it was on average achieving about 12 million tons per annum before it needed a replacement, which was a good result. So here just shows some videos of the final solution in action. You can see there we've got nice soft loading onto that outgoing belt with plenty of edge clearance between the material and the skirt plates. Very minimal spillage there. So, and very little build up on that loading spoon as well. So if we just look at some of the statistics or analytics of this chute, in particular the life of the belt, the outgoing belt, you can see here from the wear monitoring that the life of this belt has increased from approximately 8 to 12 weeks to potentially 5+ years, and that's because of that the redesigns that we made, and we were able to basically reduce the number of belt changeouts required. So by reducing the number of belt changeouts, there's an approximate saving of approximately $1.5 million or even more when you consider the extra uptime that was created by this design modification, and reduced housekeeping required to clean and maintain that transfer chute and those conveyors. So you can see there was a great return on investment with that project. And this is another transfer chute on the overland conveying system. So with this system here, with the increased belt speeds, there was a risk that we're going to see accelerated build-up. So this chute was already experiencing build-up and belt and skirt wear problems. So what it is with this overland conveyor that's traveling at high speed, close to 4.7 or 5 meters per second, material impacts this rubber curtain that's fitted with ceramic tiles, and then material builds up on there, and also in this chute that leads to eventually blockages, and then poor loading onto the outgoing belt and leading to higher skirt wear. So here just shows DEM modeling of the existing design and also the final design that we implemented. So with the existing design, you can see there we're having a lot of build-up occurring around that impact zone. Also, again, build-up occurring along the sidewalls and in the corners. That wasn't ideal. And also, when you're looking at the loading on the belt, we have like a lot of roping effects where we have material impacting the belt and then flowing up along the skirt plates that would wear the skirts out, and also lead to material building up on the skirt plates because it's compressing the material that would cause belt and skirt skirt wear issues. So here just shows on the right, you can see the final design that was implemented, where a carefully designed deflector plate was placed in there to try to crowd and contain that material, and also kick the material forward in the direction of feed to try to minimize that acceleration length and improve the presentation on the belt. So on the left here just shows a video of the existing design where you can see that material is like poorly accelerating along that belt and flowing a lot on the skirt plates, leading to problems. And then on the right here shows the final design with the new deflector plate in there. You can see there is more uniform and better acceleration of that material on that conveyor belt. There's less material pressing up against the skirt plates that reduce the skirt wear, and also belt wear underneath those skirt plates. So also as part of the export stream, we needed to increase the throughput from 1750 tons per hour up to 2500 tons per hour, and this and the export stream has two reclaimers that reclaim the material and transfer it to the outgoing conveyor belts to the ship loader. So we also had to increase the conveyor speeds to handle this higher throughput, and then we had to look at the transfer chutes, which were that required modification to handle this higher throughput. So we also looked at the bucket reclaimers, or the bridge type bucket reclaimers, where we had to look at the effect of increasing the speed of the bucket and the conveyor belt to achieve that required higher throughput. So what we did in these simulations is that we looked at the effect of increasing the bucket wheel speed at various time increments to see what effect it has on that transfer chute. Also, the carrier back as well. So you can see here, when the bucket starts to increase in speed, you can see there's a little bit more carryback occurring. Okay, so we can, optimize and examine the performance of these buckets and various operating conditions to see how it will, perform at the higher throughputs. Then we also looked at this other transfer chute here. That was another problematic one, where we had a lot of material build-up and spillage issues and wear issues on the outgoing skirts. So you can see here on the left-hand side, there's a lot of material build-up occurring on the deflector plate that would lead to undesirable flow patterns at times into a lower chute, and material loading on one side of the belt that would cause the belt to drift, led to higher skirt wear that led to spillage. So this required to be regularly washed out to ensure that it operated reliably. So what they wanted to do with this increase in capacity was to redesign this chute. So on the left hand side shows a modeling of the existing chute, where you can see there's a lot of build up on that deflector plate, and especially in that intermediate hopper, or that chute, where that material just typically grows over time and eventually starts to block the chute and leads to undesirable flow patterns. But also it causes material to build up on those on the lower skirt plates there, that leads to that extra spillage and skirt wear issues. So on the right here shows the final design that was developed, where we had a carefully designed deflector plate that captures that material and redirects it to the outgoing belt to help contain it and minimize the actual contact of material on that lower chute. We also modified this lower chute to steepen it up and open it up a lot more to minimize buildup. So here shows a video of the final solution in action, where you can see there that the deflector plate is operating very well and correlates very well to the DEM simulation results, where we've got minimal buildup occurring on that deflector plate. We have nice concentrated and controlled flow into that lower chute and onto that outgoing conveyor belt. So as a bit of a summary of what I've covered throughout this presentation, I just want to go over some of the key aspects of combining EDEM and Altair simulation tools in the process of bulk material equipment design. So by introducing EDEM into your workflow, engineers and designers can simulate and perform more advanced scenarios and case studies and enhance the quality and reliability of designs. So apart from the inclusion of the realistic effects that bulk materials have on equipment, there is also a reduced need for physical prototyping and testing, allowing for optimization during the early stages of a design process, and also faster identification of problems during operation, which can reduce design and operating costs. So that's all I wanted to cover today. I hope this has been some use for you and given you some good insights into the various Altair technologies that are available and how they can help in the designing and optimization of equipment that handle bulk materials for the reliable and sustainable supply of bulk commodities. So thank you very much for your attention. If you have any questions, you are more than welcome to email myself.